All right, so welcome everyone back to our Physics and Astronomy Colloquium series for spring 2021. It's an absolute delight and pleasure today to have with us Professor Keith Hawkins. Keith is an excellent astronomer who's currently one of the folks at really the forefront of a lot of the big data revolution that's going on in astronomy, with working with sort of huge volumes of data and finding new ways to use this to better understand our universe, especially the Milky Way and the structure and the history of our galaxy. So Professor Hawkins got his PhD in 2016 from the University of Cambridge. And he has been since 2018 an assistant professor at the University of Texas at Austin. And again, he's leading a lot of work with some of the latest and greatest surveys and telescopes out there. And so today I believe he's going to tell us especially about some of the wonderful work that's being enabled by the Gaia mission to do sort of combination chemical and dynamical studies of stars and really better sort of understand the origins of what's going on in our galaxy.
Awesome. Thank you very much for the introduction and for the invitation. I feel very honored. Okay, so yeah, as Betsy said, I'm Keith Hawkins. I'm an assistant professor in astronomy at UT Austin. And I will be speaking this afternoon on some of the work that we're doing in my research group on something we call Galactic Archaeology, and trying to use Galactic Archaeology to piece together the history of our galaxy. And I should mention, if you have any questions at any time, especially because I know this is a physics and astronomy department, a combined department, please let me know. I'm going to try my best to kind of do a kind of a longer introduction, since I know that everyone in the audience may not be astronomers, or maybe not used to thinking about at least our galaxy and its structure and evolution. And so what you're seeing here in the background is, the beautiful Milky Way Galaxy at the 2.1 meter telescope out in West Texas at McDonald Observatory that we have access to through UT. So usually in an in-person, kind of talk or in-person colloquium, the very first thing I would do is ask the audience a question. When you look up, what do you see? And the answers varied depending on where I was. I did my postdoc in New York City, and most people said when they looked up, what they saw? Well, you see lights from New York. That's the extent of what you see. Most people in New York City didn't say anything about the stars or anything about the galaxy at all. But when I lived in Ghana and was teaching middle school math and science, they would say, oh, well, you could see this beautiful milky band of stars. And so depending on where you are, you see different things. And if you're lucky enough to live in a place where you get relatively dark skies, you might see something that looks like this. So this is an image of the night sky, and you can see the Milky Way Galaxy. It's this milky band of stars, and it's really what I study, actually. And so the Milky Way is made of about 100 to 200 billion stars, and the Milky Way is of course, it's our closest galaxy because it's the galaxy that we live in. And the Milky Way also, is not just some amorphous blob of stars. We know that the Milky Way has some structure to it. And we also have some really fundamental questions, I think, in astronomy about how the Milky Way really came to be, how it formed, how it evolved, how it's structured. And that's really what a galactic archaeologist is trying to do, is trying to answer these really truly fundamental questions about how the galaxy formed and structured and assembled itself. But using fossil stars, each one of these little stars, to identify and answer, or to try and answer these questions based on those fossil stars. In essence, many astronomers study galaxy formation. It's one of the fundamental pillars of astronomy today. How do galaxies form? And so as a galactic archaeologist, I fall under that umbrella of galaxy formation astronomy, but just using the Milky Way as a laboratory for answering those types of questions. So you can answer galaxy formation questions by looking at galaxies on the other side of the universe that are extremely young to see how they're being built up. But you can also use our galaxy as a laboratory, and there's specific advantages to using our galaxy as a laboratory simply because it's so close. You can observe individual stars in our galaxy to understand how it is structured and how it came to be. Whereas in other galaxies, generally speaking, you can't actually resolve individual stars, they're just too far away. And so galactic archaeology is a wonderful term because it's a term that you can use at cocktail parties. And I get to say, I'm in the Indiana Jones of the galaxy. But, at some level, it's essentially just answering questions of galaxy formation using the Milky Way as a laboratory and using so-called fossil stars in the night sky. When I say stellar fossil or fossil star, in some sense, every star is a fossil. Generally speaking, stellar fossils generally mean old stars that are between 13 and 8 gigayears or billion years old. But in principle, every star is a fossil because generally speaking, its chemical abundance pattern doesn't change over the course of its life. And so its chemical makeup or chemical fingerprint is essentially invariant. That's not entirely true because things like light elements like carbon, nitrogen, and oxygen will change over the course of the star's life. But for most elements on the periodic table, the star's age does not change its chemical abundance signature. And so what that means is that if you look at a star that's 8 to 10 billion years old, then what you're doing is you're seeing what the state of the gas, the chemistry of the gas was doing 8 to 10 billion years ago. And the closest terrestrial example I can find to that would be like, if it's similar to ice cores, when folks go out and dig ice cores in Antarctica and look for bubbles of early Earth's atmosphere that was trapped, that's the same type of concept in the stars as well. And so these stars, of course, make up the Milky Way, and this is the kind of an artist's impression of what we think the Milky Way galaxy looks like. It is a barred spiral galaxy, barred spiral because it has a bar here in the center, and it has spiral arms coming off the bar. And so that is the type of galaxy that we live in. And our galaxy has 5 various components to it. The thick disk, the thin disk, and the bulge. We live here in the sun, and we live about 2/3 of the way out of the center of the galaxy. So we don't live anywhere near the center of the galaxy. Just to kind of orient you in terms of where we are. So we're over here at 2/3 of the way out, about 28,000 light years away from the center. Center of the galaxy is here. There's a bar in the center, and that bar is surrounded by a bulge. And then the bulge is surrounded by a halo of really old stars. And then you have a thin disk and a thick disk. And I'll actually walk through each one of these components in the introduction, just to give you a little bit of a flavor of what those components are, because I'll talk a little bit about, in the rest of the talk, beyond the introduction, I'll talk about what my group is doing in each one of these components, since we don't really stick to any one component in my group. So the thin disk of the galaxy is incredibly thin. And at the top right corner, I'm actually going to compare each component of our galaxy to a particular breakfast food, because I like breakfast, and I feel like it's actually quite easy to visualize the galaxy this way. So the galaxy's thin disk is very similar in aspect to a French crepe. It's incredibly thin, it's got it's kind of long but thin. It's rotationally supported, which means most of the stars are kind of going around the center parts of the galaxy. It's kinematically cold or cool, which means that the velocity dispersions are low. So all the stars are kind of going around in relatively nice ordered ways with relatively low eccentricity. They're relatively young stars, between 0 and 8 billion years old. They're fairly metal rich. And when I say metal rich, I really mean, generally speaking, we use iron over hydrogen to track the metal content of a star. I'll explain a little bit more of that in a couple of slides here, but metal rich, I should also mention in astronomy, anything heavier on the periodic table than helium is technically a metal. Basically because everything, hydrogen and helium are the most abundant elements, and then everything else is kind of not so abundant. So they're just called metals for short. But these are stars between 1/2 and 3 times the iron content of the sun, so that's their metallicity. And this component is where the sun lives. So the sun is involved in the thin disk of our galaxy. The thick disk, on the other hand, is a much thicker form of the thin disk. So instead of a French crepe, imagine a very fat American pancake. And it was discovered in the 1980s by Gilmore and Reed through star counts. They basically effectively counting the number of stars as a function of vertical height. If you do that, the number of stars should fall off in an exponential disk. So you should fall off exponentially. But what they realized is as they counted and went upwards away from the plane of the disk, the number of stars fell off much more slowly than expected. And in order to describe that in a theoretical way, they had to add an additional disk of stars, which was a thicker form, a thicker disk. And it was discovered by Gilmore Reed, Gilmore pictured here. And I just kind of note this for the students in the room. This is part of the reason why I chose to go to Cambridge University to do my PhD, because Jerry Gilmore was my PhD advisor. But the advantage of also going to the UK was that I did my PhD in about 2.5 years. And so I'm happy to talk to the students about kind of what that was like to kind of go through such a quick PhD and rapid succession from that to postdoc to faculty. The thick disk is rotationally supported, just like the thin disk, but it's kinematically hotter than the thin disk. So it's a lot higher velocity dispersions, more eccentric orbits. The stars are generally speaking older and therefore more metal poor as well. And so that's the thick disk of the galaxy. The stellar halo is on the outskirts of all of this. And the halo, the best analogy I can come up with in breakfast food is imagine you have your crepe that's surrounded by your fat American pancake. And then you batter that up and you deep fry it. That batter on the outside is the stellar halo that surrounds everything. And the stellar halo, stars are moving relatively fast in kind of non-ordered ways. The highly eccentric orbits, generally speaking, are generally, large, wide variety of velocities and large variety of directions as well. It's the oldest component in the galaxy. Most of the stars are between 10 and 13 billion years old. And you can find some of the most metal poor stars in the stellar halo, which would indicate these are stars that are very, very old. It's likely got multiple components, although there's lots of kind of questions as to what's going on in the stellar halo with its components. And then the final component of the galaxy is the bulge, and the bulge is kind of in the center bit. There's a bar embedded inside of the bulge, and the bulge is like kind of the butter, if you put a kind of glob of butter in the center of your pancake. Stars are moving relatively fast in ordered ways. It's a very old component of the galaxy. There's multiple components. The most recent studies from Bensby 2017, 2018, and Melissa Ness's work from Argos have shown that the bulge likely has 5 different components or potentially more, with a bar embedded inside of it, and it's metal rich. Although there are lots of metal poor stars in the bulge, but they're hidden because there are so many more metal rich stars. And one of my graduate students, Maddie Lucy, has been working on a large survey of these metal poor stars in the galactic bulge. So that's the various components of the galaxy, and this is a cartoon of the galaxy here in this corner. But this is what our galaxy actually looks like. If you were to actually go out and observe our galaxy, this is a reconstruction based on data from the Gaia spacecraft, which I'll talk about later on. This is the most modern view of our galaxy that we have to date, not including these two. This is the large and small Magellanic Clouds. These are actually smaller, relatively dwarf galaxies on the outskirts of the galaxy that the Milky Way is currently in the process of eating up. So this is our bulge, our thin disk, our thick disk, and our halo. And there's all kinds of components. There's all kinds of debates going on as to whether these components are real, and more importantly, what is the transition between the components. And I put in red down here, note that there's a debate, that there are debates in the literature still about these components. And I say this especially when I'm giving a lecture or talks in the United States, because when I was an undergrad, I was told that when I was studying astronomy, that galactic science and galactic structure and stellar astronomy, those were all solved problems, and that there were really only 2 big problems left in astronomy. There was cosmology and there was exoplanets. And then I realized when I went to Europe that just really wasn't true. There's a lot of problems, including those in galactic and stellar science. And it's part of the reason why there's a lot of work going on today regarding stellar and galactic science. Now, if you want to decompose the galaxy into its various components, the way that you would do that is through either spatial, kinematic, or chemical. I'm going to skip the spatial and kinematic because I really don't have time to talk about that. And even though I do work on all 3 of those things, but the thing I was trained on, I think early on in my career, was on stellar chemistry. And so that's the way I generally prefer to decompose the different components of the galaxy through the chemistry of the stars. And so this is kind of a nice, really cartoon picture from Anna Frabel showing how the universe chemically evolves over time. It's kind of like taking an entire course on galactic chemical evolution and condensing it into one slide. At the beginning of the universe, you've got the Big Bang. And then after the Big Bang finishes and everything starts to move away and cool down, you basically have 3 elements that exist in the universe. You have hydrogen, lots of it. You've got helium, some of it. And you've got very small trace amounts of lithium running around. And that's basically it. So the first stars that form, which are so-called population 3 stars, are metal-free. They have no metals in them. They're just hydrogen, big balls of hydrogen helium gas. And those stars will live and they'll die, especially if they're large. They will live. Large stars live and die very quickly. Small stars live and stay around for a long time. So the first stars, we think, although no one's ever seen a population 3 star, so we don't really know exactly what they are. There's a lot of theories, and most of the theories suggest that these stars are in fact quite large. And so these stars live furiously. They burn up the periodic table. They fuse hydrogen to helium, helium to carbon, carbon, nitrogen, nitrogen, oxygen. They go up the periodic table until they reach iron. Then iron is one of the elements that have one of the largest binding energies per nucleon. And so you can't fuse iron anymore to get energy out. And as a result, your star basically effectively dies. There's a lot that I'm skipping over here and brushing under the rug, but basically you get a big explosion, and that explosion creates a bunch of new elements. And the first set of elements that come out of your population 3 stars are the elements that formed primarily in the hydrostatic burning inside of the star. And then you get some elements that formed in the explosive processes as well. So the primary elements that come out at the beginning are things like titanium and silicon and calcium and oxygen and sulfur. These are the elements that are formed by alpha capture of a helium nuclei and hydrostatic burning in the star, and therefore they're called the alpha elements. So you start out with very low amounts of iron, but lots and lots of alpha, lots and lots of these alpha elements that were formed in the first generation of stars. From that polluted gas, you form a new generation of stars. Those stars live, they die, they live, they burn their elements up to the periodic table, they die, they explode and enrich the interstellar medium again. And these are called population 2 stars, since they're the second generation. And this just keeps going over and over and over again until you get many more successive generations and you build up your metal content in your universe over time. And then finally, at later times, about 2 to 3 gigayears, up to 2 to 3 gigayears, somewhere between 1 and 3, smaller stars start to form out of the gas, and you start to get white dwarfs that form, and those white dwarfs can create a new type of supernovae called type 1a supernovae, and those supernovae primarily produce heavy elements, iron and iron peak elements, so iron, cobalt, nickel, chromium, and that kind of stuff. And then those disperse out. So the next elements that form after the alpha elements are the so-called iron peak elements, and then even at later times, you can get neutron stars that form, and those neutron stars can then coalesce together and merge, and that can then produce your even heavier elements, your lanthanides, your R process elements like europium, uranium, yttrium, and so forth. So that's essentially how you get your elements. The first elements that form are the alpha elements. Then the next set of that are generally speaking the iron peak elements. Then you get the heavier R and S process elements kind of at even later times. This is a very, very cartoon, and I'm sweeping a lot of stuff under the rug here, but for the sake of this talk, I kind of wanted to describe that. And the reason why that's useful here is because one of the primary chemical diagrams that you'll see in this talk at least once is this so-called alpha metallicity diagram. And it is the alpha to iron ratio in a star on the y-axis as a function of the iron to hydrogen ratio on the y-axis. Now, this is essentially this bracket notation denotes that it is the log of the number of iron atoms in your star divided by the number of hydrogen atoms in your star minus that same value in the sun. So the sun is always normal. Everything is normalized to the sun. So the sun sits here at 0, 0. And this is logarithmic, so that -1 means you have 1/10 the iron to hydrogen content in the star than you do in your sun. If you have a star that has a metallicity or an iron hydrogen ratio of -2, then you have a star that has 1/100th the number of iron atoms in its atmosphere compared to the sun. Okay, so that's how you read this diagram. On the y-axis is the ratio of the alpha to iron ratio. And remember that the first elements that form are the alpha elements. And then the second set of elements that form are the iron and iron peak elements. And so if you take the ratio of alpha to iron, old stars, that ratio will be high, and young stars, that ratio will be low. Okay, and so the point here is just to show you that the halo, the thin disk, and the thick disk, they're all in different regions of this diagram. The halo is metal poor and alpha enhanced because they're old stars. They've only really been polluted by very big explosions that have only produced the alpha elements. They haven't produced very much iron, so they're low in iron and very high in the so-called alpha elements. Okay, so that's very useful. The other reason why this diagram is super useful is because generally speaking, the time delay between getting your alpha elements and getting your iron and iron peak elements is about between 1 and 3 gigayears. And so what happens is that if you're in an environment that's evolving chemically really fast, like you're in a big, massive galaxy that's, constantly you get explosions going off and you have lots and lots and lots of chemicals being processed in the galaxy, you can build up a lot of iron before that gigayear occurs, and you get a turnover in this alpha to iron ratio. Dwarf galaxies that are much smaller, they're really slow in terms of their chemical evolution. The need of where you're going to get that turnover in the alpha metallicity plane is going to be at much lower metallicity. So it's a way to distinguish dwarf galaxies from Milky Way-like galaxies. And so this is one of the diagrams that we use to decompose the galaxy into its various components. And I only describe this again because I'm going to use it towards the end-ish of this talk when I talk about the stellar halo. So my group at UT is the Galactic Archaeology Lab, and we work basically on every single one of these components in the galaxy in order to try and build a comprehensive picture of how the galaxy formed, how it's structured, and how it assembled itself over time. And so this is my group just before COVID hit. We've grown quite a lot since then. So I have 4 PhD students, a postdoc, and 5 undergraduate students working with me. Some of the questions that we generally try to wrestle with on a daily basis are things like, how did the Milky Way come to be? How does its components form and assemble itself? What are the key physical processes involved in galaxy formation? What are the timescales involved in galaxy formation? How do we use stars as better tracers of galaxy formation? Because generally speaking, what we're really observing is not so much the galaxy, we're observing the stars inside of the galaxy. And how can we improve upon the tools of galactic archaeology, things like chemical tagging that I'll talk about in this talk, to answer these particular questions. Okay, so these are kind of all of the big picture questions that we try to address in my group. I've only highlighted one of them. How did the Milky Way come to be? Particularly, how did its components form? Because that's the one that I'm really going to focus on. I'm going to talk a little bit about the formation, some of the work that we're doing in the bulge and the disc and the halo, and that's going to focus around the formation and assembly history of those particular structures. But there's plenty of other questions that my group is wrestling with. Generally speaking, I try to have one graduate student working on one of these questions at any one time. While we're here, I wanted to stop and see if there are any questions about what I've said so far. So you can either chat them. So I'll be looking at the chat, and you can also use the raise hand feature, and I should see that as well. So if you have any questions at any time, feel free to do either or, and I'll try to address that as we're going. Don't see any questions, so I'll go ahead and move on. So how did the Milky Way form? It's one of the truly fundamental questions in astronomy, right? And I have a comment. No, Milky Way is true. Is the Milky Way exceptional? That's a good question. What we think at the moment is that the Milky Way is not a particularly exceptional galaxy. That a lot of galaxies look similar to the Milky Way in terms of what we call L-star galaxies that have similar masses and are similarly typed. But whether or not the Milky Way is, whether or not the history of the Milky Way is exceptional, that's something that we still don't really know the answer to, and we're trying to figure out. As you'll see later in this talk, the Milky Way, you build a galaxy by eating up a bunch of small things, but that history of what the Milky Way has eaten might actually be somewhat exceptional compared to other galaxies of similar mass. So that's something that we're still trying to figure out, whether the Milky Way is truly an exceptional galaxy or if it's just like a run-of-the-mill normal galaxy. But generally speaking, a Milky Way mass galaxy is likely to be fairly common in the universe. And Milky Way, the components that we see in the Milky Way, we see in other galaxies. So there's not much of a reason to believe, at least at the moment, the Milky Way is a truly exceptional system in any way, shape, or form. So how do you form galaxies like the Milky Way? The first idea is, one of the first ideas kind of that has been cited a lot is from an idea from 1968 from Egan, Lindebell, and Sandage. And the idea basically is this idea of monolithic collapse. You take a big gas cloud and you let the gas cloud collapse due to gravity. And as it collapses, it fragments and forms stars, and you get a big ball of stars. Pretty simple idea. And then if you want to get a disk galaxy out of that, right, you need to give it a little bit of angular momentum at the beginning, a little bit of a spin. And because of conservation of angular momentum, as the disk collapses and due to gravity, it will spin up into a disk. So you can get a disk galaxy. So this is a pretty simple idea from the 60s. And, it was tested through looking at the positions and the dynamics of stars in the local neighborhood, as well as globular clusters in kind of outskirts of the halo, kind of these old clusters of stars in the outskirts of the halo. And it was found that while this theory did a pretty good job of predicting the observations that we see, it didn't quite do the best job. And so another idea came out in the 70s that showed that maybe the galaxy formed in a completely different way. This is the hierarchical galaxy formation way from Cyril Zinn. And the idea is basically of this method is that you take your galaxies and you take protogalaxies and they eat each other up. And you form galaxies through accretion processes. And so what we think nowadays, this is a simulation by O'Shea, which shows, yes, good, it started. These protogalaxies have formed, and what happens is that these protogalaxies may form through monolithic collapse or other processes, and then what happens is you get all kinds of cannibalistic processes going on, where one galaxy is eating up all the other galaxies nearby, and as it does so, it assembles and builds itself. And as it's doing this, notice that there's a lot of structure and substructure in the halo of this galaxy that's being formed. There's rings, there's streams, there's shells, there's all kinds of substructure going on in the halo as a result of these accretion and harassment type of processes going on inside of the disk, or sorry, of the galaxy as it's forming. And which of these ideas is correct will really depend upon getting high resolution data of our galaxy. And this is part of the reason why I do galactic archaeology now. We're kind of in a really data-rich era that we never have really been in before. We've entered this big data era in galactic archaeology because we have, number one, we have these large spectroscopic surveys. I've listed a couple of them here: GAISO, GALA, Foremost, Apogee, RAVE, that I work with, that are producing moderate to high resolution spectra for hundreds of thousands, if not millions of stars at a time. And these spectra are very useful because they can be used to determine not only the motion of the stars, the radial velocity of the stars, but also their detailed chemical fingerprint. And luckily, kind of as these surveys are, churning through, getting spectra for all these stars, we also have Gaia that's come online. Gaia is pictured here. It's also pictured in my background here because it's something that I use so regularly. Gaia is a space mission from the European Space Agency. It's called the Billion Star Surveyor, and its goal is to produce the most precise three-dimensional map of our galaxy ever attempted by human beings. And to do this, it will map the positions and motions for about 1 to 2 billion stars. Now remember, that's really only like 1% of the galaxy. So, this is the best state-of-the-art data that we have today, billion stars, but still it's only like 1% of the galaxy that we're mapping. And so we'll be able to pertain precise photometry, 3D velocities, and positions and distances, parallaxes particularly, for this very large sample of stars. And it was said that Gaia is going to revolutionize astronomy, galactic astronomy, and the reason for that is because imagine the galaxy looks like this and the sun is here. Now, the sun isn't really there, but imagine the sun is 2/3 the way out. Before Gaia, what we knew about our galaxy really focused on the 100,000 nearest stars within our galaxy based on data from the Hipparcos spacecraft, which was launched in the 90s. And that was kind of like this small little volume around the sun, the solar neighborhood, so to speak. And everything we really knew in terms of like detailed positions and motions and chemistry for most of the stars, not all, but many of the stars in our galaxy, were kind of in this small little neighborhood. And so Gaia is expanding us from this small little volume to a significantly larger volume, getting us to the other side of the galaxy, in fact. Granted, it's still 1%, but it's a more representative 1% compared to what we had before. And so with Gaia plus these large spectroscopic surveys, we're kind of in this unique era of galactic archaeology. see, I got a question in the chat. Was the star come first or the galaxy? Did stars come first or the galaxy? That's a good kind of chicken and egg question. I think it's believed that stars, the first stars came first, the so-called population 3 stars came first. They lit up the galaxy, they lit up the universe, and then caused the universe to reionize. But then, as more and more stars formed, they could actually form galaxies as a part of over a long period of time. Long period of time being millions or up to 1 billion years or so. But I don't work on that particular part of so-called reionization or cosmic dawn. I don't really work on that, but that's the general idea. So Gaia, what we have now from Gaia is, it was launched 2013 when I started my PhD. It was, the first data release was in 2016 when I got my first postdoc, and the second data release was in 2018 when I got my faculty position. And we've got positions for 1.8 billion stars. They were actually only supposed to do 1 billion, and they accidentally got 1.8 billion, so that's great. It cost about €1 billion, so now it's only about 50 cents per star. And the most recent data release was December last year, and the next data release will be early 2022. Just a quick warning for those of you that use Gaia data or are using it regularly. If when we're in our astronomy 101 classes, we all learn that the way we measure distances to individual stars in the galaxy is through parallax angle, and you just invert the parallax angle and you get the distance. I'm just telling you quickly, maybe don't do that if you are trying to get the distances from Gaia, because this all comes down to error analysis. If you have measured a parallax, and this is the probability, this is from Ostermather and Bather-Jones, you measured a parallax, and this is the probability distribution, or the posterior, so to speak, of that parallax measurement. Because when you do the 1 divided by the parallax, the nonlinear transform that goes into that means that you'll get if your parallax errors are 20% or 30% or 50%, doing 1 divided by the parallax, you'll get an asymmetric distribution. And so if you take the expectation value of that asymmetric distribution, you'll get a biased answer. And so you just have to be a bit careful when you're working with parallaxes. If you're working with parallaxes that are precision better than about 10%, maybe you can invert the parallax. But as you can see, as you go to 20% or even 50% parallax errors, you get a long tail in that distance posterior, which can cause issues with the resulting distances. They can be biased. Okay, so my goal over the next, over the next 15 to 20 minutes, the rest of this talk really is focused on what my group is doing on the various components of the galaxy, some of the current projects. I have a warning down here that this will be breadth over depth, so I'm not going to go into detail about any of these projects. I'm happy to answer questions in the Q&A or even after the fact, but I want to give you all a flavor for some of the stuff that we're working on, and the goal here is to see if there might be any kind of collaboration points with folks here at Kansas. So the first one I'll talk about is the Disc and Bulge, and I'll kind of group those together and talk a little bit about what we're doing in the Disc and Bulge. Particularly in this idea of chemical tagging. So there's this idea that came about in the early 2000s in galactic astronomy called chemical tagging. And as you might think, the idea is to tag the birth location of individual stars on the basis of their chemistry, of their chemical fingerprint alone. And this is a really cool idea, because if it works, right, then I can measure the detailed chemical fingerprint of every star in the galaxy and tell you exactly where it was born. And if I can do that, then I can reconstruct the history of our galaxy. Now, the important point here that you may or may not know already is that our galaxy, stars form in our galaxy likely in associations or pairs or groups. But then what happens is as they orbit in the galaxy, they interact with a bunch of junk, and they get jumbled up and they move all over the place and they move around. And then the galaxy is a jumbled mixture of stars that were born in various places. And so if you want to reconstruct the assembly history of the galaxy, how each part assembled, then if you can unjumble those bits by using the chemical fingerprint, then it would be really truly powerful. So it's like humans, right? Human beings, we migrate all over the planet, and we're now hyperconnected, so we can migrate wherever we want, or not wherever we want. I guess that's quite a political question, but we can migrate. One of the things is that how do you know where someone was born or where their ancestry lies? And the idea here in planet Earth is that you go to a service like 23andMe and they take your DNA and they can tell you that X% of your ancestry must come from, say, Africa, and X% must come from Asia, right? But this is doing that same thing, but doing it with stars in the night sky. And so imagine you have two gas clouds, right? They're separated in different parts of the galaxy. They have different chemistry. Cloud 1 is iron rich, cloud 2 is iron poor. They form stars, and then over time, what happens is those gas clouds disperse because the stellar winds disperse the gas clouds. And then the stars interact with a bunch of junk around and they disperse themselves. And so you could take a spectrum of star 1 and 2 and realize, they actually look chemically alike. Or sorry, take a spectrum of this star and find that they don't look chemically alike, so they could not have been born together. But if you take a spectrum of these two stars, well, then suddenly you realize their chemistry is alike, and so they had to be born together. And so this is the idea, right? And the general assumption of this idea is that stars born together have to be chemically homogeneous. So does chemical tagging work is asking, are stars born together? This is an open cluster, for example. Are these stars chemically homogeneous or not? And so you have two answers here, right? Yes and no. And if it's chemically homogeneous, it's assumed to be, it has to be chemically homogeneous in order for chemical tagging to work. But it's also assumed to be chemically homogeneous for exotic star characterization, like M dwarfs. So exoplanet folks are looking generally for exoplanets, not always, but a lot of them are looking for exoplanets around M dwarfs. M dwarfs are very hard to analyze because they're really cool. They have molecules in their atmosphere, and our understanding of molecular opacities is just really terrible at these temperatures and densities. And so what people will normally do to characterize an M dwarf is they'll find an M dwarf in a binary pair with an FGK star that's easier star to measure. And then they'll say, oh, well, I can measure the chemistry of the star that's easier to measure, and I'll just assume that the other star, the M dwarf, has the same chemistry because they had to be born together. Another way of thinking about this question is it's kind of like asking, are twin stars alike? Are they fraternal or identical? And so if the answer to this question is yes, then great, we're fine. If the answer to the question is no, then we're kind of in a bit of trouble. And so this question is really important because there are entire surveys that have millions of dollars worth of investment that are built around the idea of chemical tagging. So skip forward to 2017, and there was a nice paper that came out from Simon O, which showed that stars that are born together. This is a star system, two stars, binary stars, Kronos and Krios. And the chemistry of one star is in red, and the chemistry of this other star of its companion is in blue. This is the X over H ratio, X being each one of these elements. And if the chemistry of the two stars were the same, then the red and blue lines should overlap, but they don't. In fact, the iron content of these stars are different by 0.2 dex, so 10 to the 0.2 different. And so this was really scary because this said, wait, maybe chemical tagging can't work because stars born together are not chemically homogeneous. And so there's a lot of work done before this, and I've even worked on this as well in 2015. But in 2020, we published a paper where we went out and we did this. Kronos and Krios was a scary example of when stars are born together but not chemically alike. We wondered if this is a fluke or not. And so we went out to McDonald Observatory in West Texas, and we observed stars that were binary stars, one star here and one star here. And we tried to ask the question, are they chemically alike, which means chemical tagging can work, or they're not, or are they not? And instead of just doing one pair, we did 25 pairs to see how common it was to see that Kronos and Krios example. And for the spectroscopists in the room, here's an example of 4 separate pairs of stars. This is the spectra of those stars. Each one of these absorption features, of course, is caused by a different element. The dotted line is one star, and the solid line is the other star. The important point of this, the takeaway point here, is that you almost see no differences between the dotted and solid lines, which indicate that the stars are probably very similar. The summary plot is shown here, which is this is the dispersion of the difference in the X over H ratio for each of the different elements for the wide binaries and triangles compared to random pairs of stars in orange triangles, and black circles are measurement uncertainties. The point here is that if all of our stars were chemically homogeneous, if all of our pairs of stars were chemically homogeneous, then the red and the black should be similar, and in fact they are. So in almost every element, we find that we can't observe a difference. We cannot measure a difference between wide binaries, between the chemical fingerprint of two stars born together, but we can for stars that are random pairs of stars, random field pairs of stars, i.e. stars that are not born together. And so this is great news, right? So we wrote this paper in collaboration with some of my students, Drea Carrillo, who's finishing and starting a postdoc at Durham this fall. Maddie Lucy is my third-year graduate student and 2 undergraduate students. So we wrote this paper, Identical Fraternal Twins, the chemical homogeneity of wide binaries, and we found that in general, they're largely identical. In 90% of the cases, 80% of the cases, the wide binaries are chemically homogeneous. And this, of course, caught the attention of the press because I actually am a twin. And so this is me pictured with my twin brother in a science classroom. But it was like, twin astronomers study twin stars. And what's cool is that I have a PhD student, Tyler Nelson, who's actually extending this work. He's going, this is the difference in metallicity. So this is the difference in the iron to hydrogen ratios of 2 stars born together. And so generally speaking, there's almost, it's kind of centered around 0, very, very little dispersion around that. But Tyler's actually, this is as a function of the separation, how far the stars are separated from each other. And so we're now checking to see if we can go to further and further separations, do we see the homogeneity drop? And what we thought is that we would see that drop because as stars become more and more separated, at this point, you're starting to talk about stars that are separated by a parsec. That's 3.26 light years. And what Tyler's finding is that even if we go out to 10 to the 7 AU, now you're talking about 100, you're talking about 10 parsecs. You're talking about 32 light years. This data point here, these stars are separated by 32 light years, and somehow the stars are still homogeneous. And so this is really quite encouraging for chemical tagging because it says that stars born together are very likely to be chemically homogeneous, even at wide separations. So now that we think chemical tagging can work, what can we do with it? We've done a lot of different things. I don't have time to talk about everything we've done, so I'm just going to highlight some of the stuff that we did in the papers we've written on it. So I worked with Rosie Wise and used this idea of chemical tagging to actually identify the birth location of these rare and interesting stars called hypervelocity stars. These are stars that are moving so fast they're unbound to the Milky Way. Nobody knows where they're coming from. It's thought they come from the galactic center. Some people thought they were coming from a large metropolitan cloud. And so I wrote a paper where we actually used this idea of chemical tagging to figure out where these stars were born. We got a large NSF grant to do that. One of the things I do want to mention to the undergrads or graduates in the room is that this hypervelocity star project I actually started when I was an undergrad as an REU student, and I'm still working on it today. We've also, my student has been using chemical tagging, this concept of chemical tagging, Maddie Lucy, to study the origins of the most metal poor stars in the galactic bulge, try and figure out where they came from. And so she's written 2 papers finding that we know with hundreds of metal poor stars uncovered in the bulge, and some of them look like they chemically might have come from globular clusters. And most recently, we've also been looking at using chemical tagging to look at these very long streams of stars that were discovered with Gaia DR2. These are stars in the galactic disk that are 400 parsecs long, but still very young, like 100 million years old. And so I just wrote a paper with my student looking at the homogeneity of these young stellar streams to identify again where they came from. And I have a student now working on a paper in prep where I just did this with one stream, the Pisces Ardana stream. My student, Catherine Menea, is actually working on a larger number of streams using the work from Konkel and Kevin Covey. And then finally, I'll kind of wrap up with what we're doing in the stellar halo. So I talked a little bit about the chemical tagging and what we're doing in the galactic bulge. But the final thing I want to talk about is what we're doing in the stellar halo for about 5 minutes here, and then kind of open for the last 10 minutes of just complete Q&A. So one of the questions that comes out of the, I think I saw a question. How do you know these stars are born together? Yeah, that's a very good question. One way that we know these stars, this is going back to the wide binary work. One of the ways that we know these stars are likely born together is because they're co-moving. They're the only pair of stars that are co-moving nearby. And in addition to that, if you compute the relative rate of chance encounters, that is 2 stars that weren't born together that somehow just find themselves orbiting each other, that rate is extremely low. It's very, very, very unlikely because the space density of stars is just so low in the galaxy. It's very unlikely to have just random field stars in the thin disk just start orbiting each other randomly. In order to do that, it's much more likely to have that kind of thing happen in open clusters or cluster-like environments where the density of stars is higher. So it's just based on the stellar density, it's just much more likely that these stars had to be born together and are not chance encounters in that regard. That's a very good question. One thing that we need to do, one thing that we should do is actually measure the direct ages of these stars. Ages are very difficult to measure in individual stars. One thing we could do is measure the ages of the individual stars and see if the ages are consistent with each other, and they should be. Generally speaking, if you look at, we do isochronal ages, which are very crude ages, they do match, so that the ages match. But again, these are stars that in principle, you'd want to get better age precision than just isochronal ages. But that's a very good question. So the last part of the talk is really about the galactic halo. So how did the halo form? And generally speaking, we're really interested in what the role of accretion in the stellar halo is. So if we go back to that original simulation that I showed earlier, you have these galaxies are forming from, you take these proto-galaxies and you merge a bunch of stuff on it. And those accretion events create your galaxy that you see. And so the question really is, what is the role of accretion? In this simulation, it might have you believe the role of accretion is extremely important. Lots and lots of things merge, 10s, 20s, 50 things merge. But the real question is, how many things does the Milky Way eat in order to produce itself? And so this is really interesting in that this question was starting to be asked early on. People were, this is work from Nice in 2010, where they took a sample of halo stars and they asked the question, okay, does the halo look chemically alike or not? The idea being that if a bunch of stuff accreted, the material that was accreted will look chemically different because it was born somewhere else, going back to that chemical tagging idea. And so they opened, the blue and the red here are halo stars. They found them kinematically because they're moving all over the place. They're halo stars. But there were two different chemical signatures. One was alpha rich and one was alpha poor. And when they looked at the alpha poor stars and did orbit integrations, they find that the alpha poor stars, which are the red, these are the low alpha stars, they're on highly eccentric orbits, and they get far out into the stellar halo. So this is the eccentricity of the orbits of these stars on the left panel. These are the eccentricity of those orbits. These are how far out. This is the maximum radius they can achieve away from the galaxy. And notice that all of the red points are highly eccentric and they can get really far out. And so this made them argue that the red points are from many accreted systems and the blue points are from in situ, formed inside of our galaxy. And so many earlier work said that there were many accreted systems that all merged. But recently, there's been some discussion that maybe it was just one system. And that's based on the chemical signature of this particular system. I don't have too much time to talk about that, but there's been a lot of debate about whether or not it's one system or many systems. And so what we have now in terms of our idea about how the halo form is that you take a pre-existing disk within our galaxy that formed very early on, and you merge stuff onto that disk, likely one system or potentially many systems, but you merge stuff onto that disk. When things slam into the disk, they heat the disk up and puff it up into the interstellar halo. That puffed up material is called the in situ halo. And then as those merger events happen, they deposit their stars inside of the Milky Way as well, and that creates your accreted halo population, your ex situ component. And so the question really becomes, okay, did the Milky Way eat one big thing in order to form, or did it eat up a bunch of small things to form? And the Metallicity distribution of the stellar halo actually can figure this out, because if the Milky Way ate one large thing, that large thing is going to have a much larger metallicity, because it's going to be an environment where there's been a lot of chemical evolution. And so you're going to look at it, if you look at the metallicity distribution of the stellar halo, it should be metal rich, fairly metal rich. But if the metallicity distribution is fairly metal poor, that would be indicative that the galaxy ate a bunch of small things, because those small things are more metal poor than one big thing. And so one of the things that we're doing, this is the last thing I'll really talk about, is we're trying to answer this very question. Well, what is the unbiased view of the stellar metallicity distribution in the stellar halo? And this is a question that has been asked for a long time. The Longitudinal Sky Survey, for example, back in 2000 tried to do this, but the selection function, the way they selected their stars, was very biased. And so they found that the metallicity distribution of the stellar halo was very metal poor. Whereas newer results in a more unbiased way from the H3 survey from Charlie Conroy's group find that the metallicity is very metal rich. And so there's this big question, okay, well, is the metallicity distribution metal poor, or is it more metal rich? And so one of the things that we're doing at UT and in my group is we're using a survey called HETDEX to try and answer this question. HETDEX is at the Hobby Everly telescope pictured here. And these are actually the instruments of HETDEX. This is the virus instrument being used to do HETDEX. And HETDEX is done with virus, and virus is a massively multiplexed fiber-fed low-resolution spectrograph. When I say massively multiplex, what I mean there is that in a single shot on this telescope, in a single image, this image will collect 34,000 spectra. The trade-off is, in order to collect 34,000 spectra, they have to be very low resolution of like 750. And so its primary purpose, HETDEX, is to study Lyman alpha emitters and other galaxies across the universe to track dark energy. But I actually repurposed HETDEX to do galactic archaeology and stars. And just to give you an idea, this is the first data release of the HETDEX stellar catalog I published just last week or 2 weeks ago. And this is the color magnitude diagram of those stars. And more importantly, this is the spectra from HETDEX, the stacked spectra from these particular regions of the CMD. I only put this image up primarily for the astronomers in the room because when I saw this image, I thought, oh my God, this looks like Carol Nosley. This looks like our typical Astronomy 101 book, where you have the white dwarfs, the OBA stars, the FGK stars, and the M dwarfs down here. And suddenly in the M dwarfs, right, you see the TIO bands, you see the magnesium triplet here. So these spectra are really quite beautiful. And even at resolution of 750, what I show is that in this paper is that you can actually measure not only the radial velocities at the order of about 20 to 30 kilometers per second, but you can also measure metallicities. And you can use HETDEX to find metal poor stars. And in principle, you can use HETDEX to derive this metallicity distribution of the stellar halo in an unbiased way. And the reason for that is because HETDEX does not have a selection function at all. It just stares up at the night sky, and whatever falls into the fiber, it gets an image of. So there's no pre-selection done at all. And so we're going to be using HETDEX in the future to map out the stellar halo. So that's kind of what we're working on now in my group. I think that the future of galactic archaeology is pretty bright with all these large spectroscopic surveys coming out, spectroscopic and astrometric surveys with Gaia. And I think that we're moving from an era where we're moving from just doing surveys of individual tens or hundreds of stars to billions of stars, where we can now start to do tagging and chemical cartography work where we're actually mapping out the galaxy for the first time. And so I'll leave you with this kind of beautiful image that we just made in our group of the galaxy in the background, but in the foreground, you're seeing stars color-coded by their magnesium abundances, and you can already start to see the thin disk here and the thick disk popping out just by looking at the magnesium abundances of your stars. So the galactic archaeology will, I think, over the course of the next 5 years, will really primarily focus on combining the kinematic information from Gaia and the chemical information from these surveys to really find out the detailed structure of our galaxy and figure out how it came to be. So I'll go ahead and answer for questions.
Thank you so much, Keith. That was a wonderful, wonderful talk. I really enjoyed that. So we're going to go ahead and take questions, and we'll do this by having folks just use the raise your hand function. So Keith, you can also see those in the participants list. And it looks like we've got one off the bat. We'll wait a moment to see maybe if we have any student questions. All right, go ahead, Greg.
Keith, that was a really great talk. Thanks a lot. So at the end of your talk, you were talking about trying to understand if the halo was built up by kind of a single big accretion event or these multiple small ones. And this is the part where my gray hair lets me say back when I was in grad school, people were talking about the spaghetti halo. But so that seems like that may not be true anymore, but it depends on the metallicity that we end up measuring for the halo stars. But I guess the question is, what can we learn by looking at the satellite numbers around other galaxies? So from the Milky Way, from Pandas and M31, and from like Saga around other nearby galaxies, how did those satellite counts and the radial dependence of those satellites tell us about how the halo is at least being built up now? And does that inform at all what we think the past history of the halo was for the Milky Way?
Yes, that's a good question. I mean, like the you can count, for example, the number of dwarf galaxies or satellites in the nearby universe, or particularly around the Milky Way, and then You can do the same thing around M31 and try to get an idea for what the current state of what the current merger history is going to look like, the present day merger history looks like. But the problem, I think, with that in terms of the past history is that the number of satellites that we have now in present day may not necessarily correlate exactly with the number of accretion events that you've had in the past. And so the question is, I think, this is really, I think, a question for simulators. Does the number of present day satellites track closely with the previous satellites or the satellites that fell in? And if it does track very strongly with that, then maybe it is an indication. The other problem that I think that has happened, at least that I have seen at least, is that many of the satellites surrounding the Milky Way, especially the UFDs, the ultra faint dwarf galaxies, really haven't been discovered until rather recently. And so until you actually get quite deep in terms of surface brightness. And so the thing I worry about with using just count statistics of the number of dwarfs we're seeing in the nearby galaxy around our radially dependent around our own galaxy would be how many are we actually missing, and whether or not that would bias our understanding of what the merger history looked like, the previous merger history looked like. Around the Milky Way, at least now, if you take the chemistry of the stars in the interstellar halo, it appears that whatever was accreted on, so-called Gaia and Enceladus sausage system, its chemistry is consistent with something that we would think of as an LMC-like galaxy. And when you look at the mass that galaxy would have brought in, it accounts for most of the mass that we see in the interstellar halo. And so it's likely that if you just look at the mass budget, most of the interstellar halo probably formed from this one LMC-like thing that fell in versus all these small things that are falling in now, Fornax-like things that are falling in now.
Cool, thank you very much.
Awesome. I see we have a question from Alex next up.
Yeah, can you hear me all right?
Yes.
Awesome, that was a fascinating talk. I had a question. In the beginning, sort of towards the beginning, you showed a list of different alpha elements, and I saw included on there was, I think, sulfur and oxygen. Sometimes I've seen just magnesium, titanium, silicon, and calcium. Sometimes I don't even see titanium in that list. Is there any sort of rhyme or reason to the conventions?
Yeah, it's a very good question in that there's been a lot of arguments about this. So the quintessential alpha elements are things like magnesium, silicon, calcium, and oxygen. These are the alpha elements that are formed primarily in hydrostatic burning, as sometimes hydrostatic, sometimes explosive. Like magnesium, oxygen, I think, are hydrostatic burning. Silicon, calcium are explosive burning. But sulfur sometimes isn't listed because oftentimes it's not measured. It's not measured because it's oftentimes the lines are, generally speaking, in the near infrared. And titanium is a weird element. So titanium is oftentimes added in the alpha element category because it behaves like the alpha elements. It has this general structure. But if you read like the annual review from Nemoto 2013 or the work of Chaki Kobayashi, you'll find that titanium actually forms from decay processes similar to some of the iron peak elements. And so titanium is actually oftentimes classified as an alpha element when it should be classified as an iron peak element. But because it behaves like an alpha element, it's classified that way. So originally the alpha elements were quintessentially described on the basis of being formed from alpha capture processes. But then there was a time period when it was just anything that followed this general structure, that was in this general same alpha metallicity plane structure. And now it's kind of, people are kind of going back and forth between them. So the conventions seem to be changing a little bit here and there. I still add titanium as an alpha element, but then always put a footnote about its origin being more of an iron peak-like element, because I think that that's important to note. But that's generally speaking, that's what the conventions are.
Thank you. That was really helpful.
We have a question from Yoni now.
Hi, thank you for a great talk. It was really, really enlightening. In exoplanets, I think the most important thing that everyone's sort of waiting for is the full Gaia data release, because that gives us the individual imaging epochs over the entire baseline of the mission. What do you expect to get in the sort of galactic archaeology field from EDR3 and DR4, et cetera?
Yeah, so right now we have parallaxes for 1.5-ish billion stars, positions on the sky for 1.8 billion. Then that's EDR3, I should mention. And so the proper motions are pretty good, actually. They're starting, we're starting to see the light of micro arc second level precisions on the parallax, which is fantastic. What I think a lot of people are waiting for in galactic archaeology is actually the next data release. In that data release will come not only the photometric epochs, but also the BPRP. So BPRP, you get the G-band photometry, the whole wideband filter photometric epochs, but then you also get the spectra, the BPRP spectrograph. So these are low resolution R of 100 spectra, R of 100-ish spectra that get integrated to give you the BPRP. And one of the things that I'm most excited about is my work with HETDEX. HETDEX is R of 700, so it's really low. It's really, really low compared to what you'd want to do with anything with stars. And in fact, when I started working on HETDEX spectra, I was told, you shouldn't even worry about the stars with HETDEX because no one can use it for anything because it's just so crappy. But what we're finding is that if you apply machine learning algorithms, like, we use TSNE, manifold learning, but you can also use neural nets to do parameter estimation. You're finding that even at R of 750, you can do really, really good work. You can actually measure temperature, gravity, metallicity, and other things. And so what I'm really excited about is the BPRP spectra coming out for individual stars, where you can actually use those spectra to measure things that initially people thought was just completely unmeasurable. And we're also really interested, I think, in the upcoming data release of the refined parallaxes and proper motions, where we can actually do work in relation to finding substructures in the stellar halo and the stellar disks as well. So the improved proper motions, the improved parallaxes, and the spectra are probably the three most important things that I think people are looking forward to in galactic archaeology terms for the next data release. And I think a lot of people are also looking forward to the so-called light curves, although they're going to be very sparsely sampled for Gaia compared to what you might want for exoplanet work.
Thank you.